Okay, so let's start my morning session on Tuesday. So I'll make the question and proposal. So the first talk is given by Professor Moon, Pilkyung Moon, from NYU Shanghai. I know it's crystalline with some state and nonlinear diagram of the Waals. Okay, so please.
Yeah, thanks, Chairman, and thanks, organizer, for inviting me here today. I'm Pilkyung Moon from NYU Shanghai campus, and today I would like to talk about the quasicrystalline resonant state and the nonlinear Venn diagram in Van der Waals superlattices. So this is an outline. The first part, I will talk about the basic theoretical model. Basic theoretical model and resonant quasicrystalline states. And just for my personal interest, I will briefly talk about the center of quasicrystal. And in the later part, I will talk about the nonlinear Venn diagram. With the discovery of graphene and two-dimensional material, we can make a new kind of superlattice by stacking it along the vertical direction. This unique structure enables us to make an extra order along the in-plane direction, because whenever there is a difference in lattice period or lattice orientation, there always arises an extra periodicity, which we call moiré interference pattern. The period of a moiré pattern is much longer than that of constituent materials, so it allows us to access the physics far beyond the limit of conventional materials. Moiré pattern is quite common in real life, and the similar thing happens in microstructure as well. For example, by stacking two layers of graphene and twisting them with an arbitrary angle, say to 1 degree, we can change the Fermi velocity and even the size of the energy, characteristic energy scale. And yeah, we can even make the superconductivity in this system. We worked in collaboration with Victor Cosino and Professor Song. We worked on this topic for more than 10 years and revealed the unique selection rule. For example, the transition between first Banach singularity is exactly forbidden by the lattice symmetry, and the stacking configuration depends on physical property, and why I cannot see this. Yeah. But most of them, all of the researches conducted so far have been done in low angle twisted bilagraphy, and there is a reason, because the period of a moiré pattern becomes low as the rotation angle decreases. The period becomes 10 nanometer in the 1 degree twisted bilagraphy. But as soon as the angle deviates from the small angle, for example, 10 degree, 20 degree, the moiré pattern period becomes compatible with the period of monorail graphene. So it's usually not very interesting. However, twisted bilagraphy with exact 30 degree is special because it does not have global periodicity. Although we can see similar patterns, but they do not appear in the periodic way. In fact, this is a quasicrystal structure which does not have a periodicity. And we had a glance of such feature. Here I plot the density of state of twisted bilagraphy for various rotation angles, starting from 1 degree to 30 degree, near 30 degree. This is a Dirac point and the conduction band and valence band side. Some features are universal to every angle. For example, this is the band opening by two-wave interlayer interaction. That's the typical interaction you see in the K-space Dirac cone interaction in twisted bilagraphy. And it's common in every angle. This is the band opening by intralayer interaction, which couples two states in the same layer, assisted by the scattering mechanism in another layer. Actually, intralayer coupling is also exists in the low angle twisted bilayer graphene, but it becomes prominent only at the higher angle structure. Finally, this very sharp heat, but of similarity is prominent only in the very close vicinity of 30 degrees. That's actually turned out to be the quasicrystalline resonant states. What is quasicrystal? Quasicrystal is a unique system which is ordered but not periodic. So it is expected that it can provide important insight into the effects of atomic ordering between periodic crystal and amorphous solid. But to study such challenging topic, the number of quasicrystal in nature is very small. Only about 100 solids are known to form quasicrystal. However, we show that by stacking 2 layers of graphene at 30 degrees, we can design and make the quasicrystal structure. This is a TM image and RPS image measured in experiment, and we calculated the electronic structure. Yeah, to investigate the electronic structure, we need to build a theoretical model. Although Van der Waals quasicrystal is quite new, but there have been almost 40 years of study on quasicrystal, on 3-dimensional quasicrystal structure. But all of them have used non-physical or some artificial approximation. This is because quasicrystal is non-periodic, so you cannot use the block periodic theorem. So they apply the artificial periodicity. For example, if we apply this to our system, we may use twisted bilayer graphene, periodic twisted bilayer graphene near 30 degrees. For example, 29.99 degrees, 02 degrees, they have periodicity. But you can see even a small deviation from 30 degrees gives a completely different spectrum. So it's not guaranteed that whether 29.99 degrees is exactly same as 30 or not. And some use the finite structure. For example, we can use bilayer graphene flakes stacked at 30 degrees. So it's something molecule-like calculation. This also gives the results, but they all have a drawback. For example, if you apply artificial non-physical periodicity, so this is the actual wave function, and this is the wave function of a periodic approximant. You can see local configurations are same, but it gives periodicity and loses the long-range order of quasicrystal. And the finite structure also gives the wave function similar to the actual wave function, but it turns out that it gives a spurious localized state at the boundary. So we developed a theoretical model that does not rely on such non-physical assumption. For this, I started from the interlayer interaction between 2 incommensurate lattices. The interaction between 2 lattices is written in this Hamiltonian. So K states in layer 1 interact with K tilde states in layer 2 with the interaction strength determined by the Fourier transform of transform integral. And also, it happens when K and K tilde matches some momentum conservation condition. This is called the generalized Unclass scattering condition. It has been extensively used in double Wall nanotube even before the discovery of Waals superlattices, and it's now very popular in this system. So the Hamiltonian looks like this. The diagonal components are just the intralayer component, and off-diagonal component shows the Unclass scattering. However, in a typical conventional Waals superlattice, we choose subspace from K and K tilde to be periodic with the global periodicity because the theory depends on the Waals period. However, there are many systems which does not have periodicity or have more than two different choice of moiré period. So I define the new subspace. Find the subspace for K and K theta, verifying the generalized Ookla condition. Starting from K naught in layer 1, it scatters to K theta, which satisfies this condition. And it scatters back again. And we can write the subspace in this way. However, the actual subspace would be just a subset of these spaces because the Brion zone of each layer is translationally invariant with respect to its own reciprocal spectrum, which means that the K state in layer 1 is equivalent to the K plus G states in the same layer. Please note that this does not happen in layer 2. It only occurs in its own reciprocal spectrum. So the optimal subspace is written in this way. And K in layer 1 is this expanded by the G vector reciprocality spectrum of layer 2, and K in layer 2 is expanded by the vector of layer 1. So unlike the periodic choice of subspace in the periodic system, we choose the subspace in the primitive lattice vector, and the K and K tilde do not overlap. By doing this, we can develop the theoretical model for general configuration, and it makes a type binding like form in the momentum space. And so the formula says that K, that point in layer 1, is expanded by the wave vector, the reciprocal wave vector of layer 2. If we map this to the first Brion zone, they are mapped to this point. And it is consistent with the RTS measurements. And we calculated the band structure. Since this is still twisted Waals graphene, we only have 4 independent Dirac cones, 2 from upper layer, 2 from the lower layer. However, because of the geometry, 12 Dirac cones gathers at a single point in the momentum space and form new series of band structure. And here is the wave function in the real space, which satisfies the quasicrystalline symmetry. So where this quasicrystalline state comes from? To show this, let's take a look at the dominant interaction in the low-angle periodic twisted Waals graphene. This is an interlayer interaction, and you can see there are 3 terms which are associated with different wave vector. First term has a wave vector of 0. Second term, third term have G1M, G1M plus G2M. G1M reciprocality spectrum of moiré superlattices. This means that single state in layer 1 couples with 3 states in another layer. However, as we've learned in our undergraduate physics and even chemistry, the interaction between 2 states becomes prominent when their energy becomes closer. Remember the picture of bonding and anti-bonding. So usually at most wave vector, these states have completely different energies from these 3 states. That is the reason why at most wave vector, the electronic structure of twisted Waals graphene is just a decoupled structure. At specific wave vector, however, one of the state becomes degenerate with the layer 1 state. At that point, band opening and Van Hoff singularity appears. That is the interaction in low-angle twisted Waals graphene. In a quasicrystal configuration, however, single state in layer 1 degenerate with 2 states in another layer at the same time. And these states also interact with these 2 states. And finally, 12 degenerate states makes a closed loop interaction. That is the origin of the resonant interaction. And this is possible only in the quasicrystalline configuration. And yeah, we can make the quasicrystal by stacking hexagonal layers in a 30-degree configuration, or 8-fold rotational symmetry by stacking square lattices at 45 degrees. And then we can get the resonant state if and only if the major interaction occurs between the atomic orbitals with the same magnetic quantum number. This is because the interaction between atomic orbitals with the angular momentum L and N are described by transform integral and its Fourier transformation with the term of magnetic quantum number difference. So if they are different, then the interaction chain are not uniform. So it will not give the quasicrystalline rotational symmetry. So yeah, atomic orbital with the same magnetic quantum number means the same thing happens not only in graphene but also in TMDC and so on. And yeah, this is the mirror space lattice, and this is the nonlinear states involved in the calculation, the combination. So as you can see, the relative point of lead points with respect to the lead Brillouin zone, and the relative coordinate of blue point with respect to the blue Brillouin zone. These all states are all degenerate, and they are coupled by the reciprocal lattice vector of each layer. So they satisfy the momentum matching condition. If we apply interlayer potential asymmetry, most of the states still keeps the mixing between two layers. However, the center states, which was originally degenerate, are completely become layer polarized, even with a very weak layer asymmetry. And here I plot the density of state as a function of energy and interlayer interaction strength. The white line, dashed line shows the configuration of a graphene quasicrystal. The quasicrystalline state is not the only state at that energies. It coexists with the decoupled states and also many other two-wave mixing states. So it's quite difficult to observe the quasicrystalline states alone. However, if we increase the interlayer interaction, for example, by applying pressure or using other material with larger interlayer interaction, then the intralayer interaction opens a gap and opening throughout the Brillouin zone and excavate the resonant states. So it would be much easier to observe. And also, yeah, investigate the double moiré structure. But yeah, this is the schematic coupling in the bilayer quasicrystal, and you can easily imagine that we may make an 18-fold rotational symmetry by stacking graphene at 3 layers of graphene at 20-degree rotation. Actually, this shows the coupling feature in the schematic Brillouin zone, and all 18 points. Clearly, yeah.
I mean, about the dispersion energy that you told us. It's about true quasicrystal state. I mean, in quasicrystalline. I'm asking this question if you consider it in an approximate limit. I mean, suppose some 21-degree approximate or larger angle approximate.
Yeah.
Then do that dispersion energy, or let's say, or unfolded, let's call it unfolded dispersion energy, changes drastically or not?
Near 30 degree, 29.98 degree, it's almost the same.
But what about 21, for example?
21 is completely different.
Okay.
Because the size of Brillouin zone, reduced Brillouin zone is the point where the band folding, and usually at the point of band folding, there occurs band opening. So the feature is different. As you can see, the density of state profile as a function of. Yeah, so these 18 states satisfy the momentum conservation condition. However, the interaction strengths are different. The interaction between adjacent layers are much stronger than the interaction between distant layers. So this is not uniform and symmetric one-dimensional chain interaction.
So this is a 20-degree rotation.
2020. Yeah.
20.
20. So it satisfies the momentum condition, but not the intensity. However, if we stack another layer, the red layer on top of the blue layer, then it satisfies the momentum conservation, and also the interaction strength becomes equivalent, identical. If you do this, continue to the infinite z direction, then we can make the resonant state with spiral symmetry. Just for fun. Such chiral structure is not very common, but there are several examples, and it is expected that many interesting feature arises in such structure. And here I plot the band structure by keeping T0 at some value, and that over theta equals 20 degrees. Clearly, there are features, band feature, which clearly deviates from the monolayer band structure. Yeah, it reminds us the quasicrystalline resonant state in a 30 degree rotation angle. But interestingly, this feature at what I call Q18 point is different from the feature at this point, which means that there may be more than more than one quasicrystalline resonant states. We can easily find such condition, where such resonance occurs by applying two conditions. All the k vectors involved should be degenerate monorail state, and they must be coupled by the momentum of each layer. By doing this, I show that each chiral twisted violet graphene actually has infinitely many such resonant coupling and different wave vectors. And interestingly, the resonant state in each layer, each chiral twisted violet graphene can have up to 4 different rotational symmetry, which means that even in this, so this shows the reciprocal lattice space and the monorail state involved in the coupling. But although this is a 12-fold rotational symmetry, but it also has a 4-fold rotational symmetry with in addition to the 12-fold rotational symmetry. So this is the coupling that I showed in the previous part. And this is also another resonant state. You can see the relative coordinate of red points are same as relative coordinate of blue points with respect to the blue hexagonal view and so on. And they are coupled by reciprocal lattice vector of each layer. So this is the reciprocal lattice vector of red and blue layers, which means that these 4 states couple and make a 4-fold rotational symmetry. N equals 5 have 4 different rotational symmetry.
So what is the emergence means?
This is the coupling stress. So this is the strongest, and this is 48, so it's much weaker, but probably observable. But 12, 4, they are almost invisible. So it's not different from the decoupled states.
48 is still I think large.
Yeah, it's
do we have any peak-like structure?
Yeah, it has, but it's a higher energy than our common states.
But you ever calculated for energy?
Yes.
So where is it?
I didn't show because our band structure is plotted by using this as center. This is mapped to the gamma point, so but this is away. So I did not show the band dispersion, and this is the wave function. Please note that this is a hexagonal structure, so 30 degree rotation means 0, 30, and 60 degree. And 60 degree is same as 0 degree. So the periodic unit is simply twisted bilagraphic quasicrystal. So except the momentum along the z direction, in-plane features are common to the twisted bilagraphic. So this will be observed in twisted bilagraphic. So this is, I already showed, and this is the wave function of a four-fold rotational symmetry. Please note that four-fold rotational symmetry can commute with periodicity, but it does not always guarantee that four-fold rotation is always periodic. This is actually the example of four-fold symmetry without periodicity. You can see this feature is similar to this feature, but they are not identical. It's still quasicrystalline structure. Yeah, the band dispersion and all of them, regardless of the angle, they are all written in a one-dimensional chain form, described by rotation quantum number, and it clearly exhibits the optical selection rule. Yeah, that's all. That's all for the first part. But before I move to the next part, let me briefly talk about the center of quasicrystal. This is the TM with the overlap of the mathematically known pattern of 12-fold rotational quantum quasicrystal. But in the absence of such support line, it's quite difficult to find such center in the TM image. So that was the one of the topics that we discussed when we did this paper, when we analyzed the experimental data. Yeah.
I mean, what was problem?
Pardon?
What was problem? I mean,
So where is the center?
okay. I mean, this is a sample tiling. Am I right?
Center, yeah.
I mean, there is some role that, I mean, if delta is less than some delta C, two hexagon, if you somehow move it.
Yeah. It's a self-similarity.
Okay.
Yeah. So because of this, so uniqueness is simple. Presence was a little confusing, but because of the self-similarity, we could skip presence in this paper. But yeah, let's talk about the uniqueness. So uniqueness, the proof of uniqueness is simple. So use schematic structure. First layer have a radius constant of A1, and second layer have A0. And delta is the local in-plane displacement between layer 1 and layer 0 and layer 1. Suppose we have a coincidence of two atoms, say delta equals 0 and arbitrary origin. Then question on the uniqueness is there any other point which have delta equals 0? Yeah. But if such O prime exists, then the vector connecting O and O prime will be the period of the system, which contradicts the definition of quasicrystal. So the exact center is unique if it exists. So this is quite trivial. Presence. So the question is, if we stack two graphene layers at 30 degrees, will there always be exact center with delta equals exactly 0? So in one-dimensional analogy, if we stack two layers at arbitrary configuration, will there always be delta equals 0 point? Yeah, at that time we discussed very briefly, but we didn't care this much because of the self-similarity, so we can avoid it. And we naively thought that there will be, because this is infinite structure, so there will be somewhere which had a delta equals 0. But it turns out that it is not. The proof of along this direction is not simple. It's simple, but it's much easier to change this to equivalent problem. So instead of starting from delta, given delta naught and looking for delta equals 0, start from delta equals 0 at O prime and ask whether the origin can have any value of delta naught. Please note that these two are equivalent, identical problem, because you can move the upper layer to match the lower layer. Okay, so delta naught, starting from this O prime, is given by linear combination of A0 and A1, which means that delta naught, its value will be, can have an infinite number, infinite element, composed of two integers. So although this is an infinite set, but its cardinality is different from this delta node. Delta node is real number. Oh, yeah, I was afraid of this compatibility. I'm using Windows and this is Mac. Yeah, so the cardinality of a real number is Aleph1, while the cardinality of two integer is Aleph0, the same as a one integer. You may consider cardinality as some kind of density of an infinite set. So although they are both are infinite set, but their cardinality are different. And N1, Aleph1 is larger than Aleph0. So the presence of exact center is not guaranteed, which means that if you take two layers of graphene at 30 degree, and if you stack once more, their microstructures might be different by this amount. Of course,
in addition to this mathematical discussion, that in the real material, we probably need to also consider the lattice relaxation.
Yes, right.
Like yesterday, Professor Aquashino has already mentioned, if delta equals to 0, that corresponds to AA stacking, right?
Yeah.
So that energy cost will be the highest. So that is that possible that for 30-degree stacking, and that the system will try to avoid to generate delta equal to 0 point. But then I guess that would be some domains if you avoid that.
Yeah.
So if you have a delta equal to 0 center, so which means the entire sample will be a single domain. In whatever sense of the domain, right?
No.
So if you allow the lattice relaxation, is that possible that the system will undergo a very tiny relative shift of each other of the two levels, try to avoid a real center, but then the system will be divided into several different domains in order to reduce the
Yeah, it is possible. It is actually, as Koshino mentioned, it avoids AA.
Right.
You need a way to escape. There is no way to escape. Not much way to escape because the unit state is very small. So in the low electricity, it can escape, right? It is also escape, but very little, almost not identified.
That's interesting.
Very small. Yeah, so if you stack if you make two graphene quasicrystal, their microstructure might be different. But unfortunately, this will not affect the band structure and physical properties, or almost visible.
So if we go to very, very infinite quasicrystal, I mean infinite quasicrystal, then delta becomes so dense. Am I right? I mean,
Delta becomes dense.
I mean appearance of delta.
It would be the probability would be distribution would be continuous.
It is completely even. I mean flat, and it is dense. I mean, it's in a sense that in an infinite quasicrystal, then I mean, you know, if you have a small quasicrystal, but just shifting two layers, I am assuming that I can prove any configuration. Just shifting one unit cell.
Yeah.
You can assume, but when you are going to very, 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 I mean, infinite, it is then all of delta somehow it seems for me, I mean, it seems that.
Yeah, that's our first understanding or assumption. And we encounter this also in the dual space tight binding model, but the conclusion is it will not show the single twisted bilayer graphene quasicrystal will not show every local configuration. Although it's almost it's infinite, so it's the delta is quite dense, but one graphene quasicrystal and another graphene quasicrystal local structure are different, and single crystal will not show every configuration. Of course, it's different. It's very tiny, so it's not talking of physics, but mathematically they are different. Like this.
So
In graphene, actually, I think that this kind of arguments will not affect any physical observable. You know, for example, your arguments, we have discussed so long time. So if you move the infinite amount of the upper layers, then it corresponds to the shear protocol in the experiment, observable. So if you have a finite energy pulse, or if you have an end of a different configuration, you will have finite shear protocol. If you end up with the same configuration, you have a zero shear. It's a full transmove structure.
Yeah.
So in the graphene, even though you said that this is equivalent, then maybe, but it's the quantum theory. It's you have always you can find same structure with the amount of very small picometer error or something like that.
Yeah.
So we are sure that the zero point shear point. So all shear point should be zero. However, if your argument seems to be very nice, so can you think about some material that depending on the quasicrystalline order, whether there is a difference in the shear point?
Not yet, but actually, so although I studied this in a quasicrystal, but this is common to even theoretic model structure.
But incommensurate or
Incommensurate.
Yeah.
Commensurate always have the same O, but incommensurate case, generally, the formula is exactly the same. The local configuration displacement is a set of real number, and the what lattice spanned by the lattice constant is finite, not finite, infinite, but it's left with zero. So even in for example, the 3-degree twisted by the graphene, the exact central coordinate will not appear in the space. So if we can see something in the, for example, phonon signal in the graphene quasicrystal with different coordinate, we may do this in the more easier system. For example, 27 degree, I don't know, 21 degree is the smallest twisted by graphene. I think its translation effect is largest. Of course, we did calculate the band structure, but its difference is smaller than 4 MeV. So we neglected it, but I don't know whether there is any signal that's very sensitive to such differences.
Another question, sorry. Yeah, so could you prove mathematically, for example, I start from assumption that there is a unique center, the uniqueness is already proved. And let's assume at the beginning there is a center, right? So then you apply a relative shift, only shift, not rotation. So we keep the 30 degree, but apply a relative shift between the two sheets. So could you prove that the center is can only like move in the 2D plane, but not disappear? It's like a wild point in the K space that once you generate it, you cannot cannot destroy it by simply apply a shifting.
Right. But
is that possible to prove that?
No, but because this displacement is continuous, but this is discrete. So even in this case, even if we start from all the coincide state and slightly move it, it will sometimes
it's not a continuous shift. So I understand it will jump to somewhere else.
No. There is a case where it totally does not exist in the space.
I see.
So I think I know the white point should be kept, but I think
no, it's not just an analog. It's not exact same with the white point, but this time if you apply, but at least if the shift is a rational number, right? So then it will jump to
right. If it is rational number, it jumps to somewhere.
Right. Yeah.
But I know because I personally love this. Anyway, so this presence did not affect the actual analysis of TM because although, yeah, as you mentioned, although this is exact center and they are not exact center, but they are similar, mathematically similar in the quasicrystalline pattern, which means that although if you just see this pattern, this looks the only center, and this will not work as center. But yeah, if you overlap another quasicrystalline pattern, you will see that they seamlessly appear. So because of self-similarity, we do not need to worry about the analysis of TEM. Anyway, so let's move to the nonlinear Landau Venn diagram. Actually, we did this almost 7 years ago. But yeah, because I was working on the quasicrystal and my Jürgen in Germany was doing another work, and it took quite some time. Anyway, so we know that electrons on the magnetic fields make discrete energy levels or Landau levels. And the energy spacing of Landau level varies with the different material. For example, bilayer graphene has almost uniform spacing, while monorail graphene has different level spacing. The conventional So the conductivity peak plotted in the magnetic field and electron density space is called the one-year diagram or Landau Venn diagram. The conventional Landau Venn diagram can reveal the period of underlying crystal. And also it can reveal the degeneracy of energy levels and also the symmetry of bands. But it cannot tell the magnitude of field dependence of the gap. Let me explain this briefly. So we can reveal the period of underlying crystal. The peak in the longitudinal conductivity are periodic with respect to 1/b, just like the Cherenkov-Haas oscillation. And it gives the area of a relevant structure. So we can identify whether this feature is from the moiré superlattice itself or from its chemical distortion. And it can reveal the degeneracy of energy level. This is the schematic extended Brillouin zone of twisted bilayer graphene. And because of spin belly layer degeneracy, electron below Banach singularity are eightfold degenerate. And yeah, this is the conductivity plotted in the electron density and magnetic field. And this is the Dirac point, and this is the end of the first band, and there is Banach singularity at around this point. Below the Banach singularity, we have electron-like Landau level with eightfold degeneracy. Beyond the Banach singularity, however, we have a hole-like Landau level with fourfold degeneracy. The difference comes from the topological Lipschitz tradition. So here I show the reduced Brillouin zone, and there are two independent orbits. Although there are only two of them are independent. In addition to these two, we have a spin and belly degeneracy. So it gives an eightfold degeneracy. As energy increases, the orbit grows and crosses. In the presence of magnetic field, one electron jump from one orbit to another to make the two orbit becomes a single orbit rotating in an opposite direction. This is the reason why the degeneracy is halved as it passes the Banach singularity. At the same time, interestingly, in addition to the eightfold degeneracy, there are some features which shows the lift of degeneracy. Can you see? This is although this is this experiment was done in a single gate system. So single gate potential not only increases the electron density, but also increases the potential asymmetry between upper and lower layer. So that lift of layer degeneracy is reflected in the additional peaks. However, we do not see such additional peak because beyond the Banach singularity, because the layer degeneracy is already consumed when it formed the topologically changing the bands. There is no such splitting beyond the pharmaceutical. Anyways, this is what we can do in the conventional Landau Venn diagram, but we cannot tell the magnitude and the field dependence of that. This is simple. So here I show the schematic Landau level structure as a function of magnetic field and the electron energy. You can see the gaps may be different. If you plot the density of state along specific magnetic field, it looks like this. So the spacing between E1 and E2 may be different from E2 and E3. However, if you integrate the density of state, you get electron density. And there, the change of electron density at each Landau level are exactly same. Because each Landau level, regardless of its energy, contributes the same amount of electron density. Of course, except the additional degeneracy vector. This means that although their energy spacing are different, but they appear with equal spacing when you plot in the n electron density magnetic field diagram. So we get straight lines in the magnetic transport measurement. This is the reason why, although the electron energy spectrum of twisted bilayer is very complicated, but it appears in the straight lines in the NB diagram. However, we showed some non-linear feature in the longitudinal conductivity and the whole conductivity of graphene boron nitride. So this is the charge neutrality point, and this is the first end of first band, say milli-Dirac point. And at most points, we see linear Landau Venn diagram. But here, we can see some lines which deviate from the linearity. It becomes clear in the whole conductivity. And this is not the only sample. The experimentalist did another shot in another sample with the same geometry. And it was consistent and reproduced, and it shows the non-linear lines. I calculated the density of state. This is the experimental result in this region. And here I plot the density of state, which usually, somehow follows the longitudinal conductivity, plotted in the energy scale and the electron density scale. Here we clearly see non-linear feature. So we know that we can reproduce this in the theoretical model. And now let's investigate its origin. This is the conduction band structure of graphene boron nitride, and green, orange, blue shows the first, second, third band. It is plotted in the hexagonal brilliant zone of the graphene moiré superlattices, and the X and Y are independent corners of the brilliant zone. Interestingly, there are band opening at the brilliant zone corner. However, the band opening at corner Y is almost negligible, very small. The reason why we get band opening at the brilliant zone corner is the moiré superlattice potential couples the monolayer states at the X corners. At the same time, it couples the monolayer states at the Y corners. However, the matrix element between X corners is finite, while that of the Y corner is almost zero. That is the reason why the band opening at X is large, while that in the Y is almost negligible. So 3 bands almost touches at Y point. Here I plot the energy contours, starting from lower energy to upper energy. This is the first band, and as energy grows, the first band disappears and the second band appears. And at this energy, we can see the coexistence of the second orange band and the third blue bands. At this energy, third band make a pocket at X corner and Y corner. But at X corner, the second band and third band are separated in energy, so as in the along the momentum direction, k-space direction. So the x pocket, which we call alpha orbit, is well separated from the second band in the k-space. The pocket at the y corner, which we call beta orbit, is almost in touch with the second band. So in the presence of magnetic field, the alpha orbit makes a closed orbit with discrete energies. But this beta orbit makes because of the magnetic breakdown, it can jump to the second band and hop again to the third band and makes an open orbit. The Landau level of such open orbit is almost continuous. So this system has two different sets of Landau levels with a completely different energy scale at the same energy range. And as you can see from the simple crossing of a solid and dashed line, which show the beta and alpha orbit, the alpha and beta almost do not meet up to the complete filling of the third band. N equal 20, N equal 12. Okay, so compared to the conventional case, what kind of difference will such continuous spectrum make in the 1D diagram? Because of such continuous spectrum, the integral from E1 to E2, the electron density difference is the integral of density of state of alpha and density of state of beta. The first term simply, alpha is the conventional discrete level, so it simply gives the Landau level degeneracy of the usual Landau level. But the second term is the term which scales with the energy difference of alpha level, lower and upper. As you can see, in the absence of beta level, the electron density does not change in the gap because there is no electron inside. But in this system, there are electrons, so even in between E1 and E2, the electron density changes, and that change scales with the energy difference. Yeah, full occupation of alpha orbit, it is nonlinear trajectory if the energy difference or density of state of beta or both are nonlinear to beta. And this shows that energy difference are encoded, embedded in the electron density difference. In addition, most importantly, we can decode energy spacing information from the information of electron density difference. So we can get the inverse formula of this, and from here we can get the energy difference from electron density difference, which is normally impossible in the conventional magnetic transfer measurement. We can apply this to several cases. The first case would be any two-dimensional material of interest approximated with well-investigated material with much smaller level spacing and known level state, such as metal, PVC, and so on. And our current situation would be case 2, a single system having two different sets of Landau level with different level spacing. To get the energy spacing of alpha level, we need to know the density of state of beta in advance. However, this would be possible in the first situation because we may use extensively studied metal or 2D and so on. However, in our system, it would be challenging because we do not have any information on d alpha and d beta at the same time. However, we have a very strong clue. For example, the total density of states, d alpha plus d beta is almost the same as the density of state of pristine graphene. This is justified because the conduction band of graphene boron nitride here, the density of state of graphene boron nitride is almost the same as monopolar graphene. On the contrary to the completely reconstructed balanced band side. And second clue is beta. Density of state of beta is much larger than that of alpha. So D plus alpha, D plus beta is almost D plus beta. This is justified from the fact that beta of the Fermi surface is much larger, as we can identify in the calculation of plane structure. And also we can identify this from experimental results. The peaks of longitudinal conductivity of alpha orbit are periodic with respect to 1 over b. It gives the, just like the shrink of the Hus oscillation, it gives the Fermi surface area of alpha orbit, and if we divide it by 4 pi square, we get the electron density. Here I plot the sum of second and third band, starting from the first Dirac quantity. Okay. And note that alpha plus beta is second and third band. And blue and red lines shows the electron density of alpha orbit calculated by theory and then extracted from experiment. They are consistent, and it's much smaller than the overall density, which means that density of state of beta is much larger than that of alpha. By combining this, we can show that density of state of beta is almost the same as crystalline graphene. It's crude but reasonable approximation. By integrating this, we get the function of N of E and get the first function and plug this to map the conductivity peak of longitudinal conductivity, transport measurement, to find the energies. Good. Landau vector, alpha Landau vector. That's all. Thanks for your attention. Right.
Hi, very interesting talk. For the first part, when you talk about the quasicrystals, I was wondering for these very interesting band structures, any interesting dynamical properties in terms of physical measurements of band, and is it insulated, is it metal? That seems like, yeah.
Yeah, but I only calculated the optical conductivity and showed the resonant, the optical selection rule. But the transport, yeah, we know that the quasicrystal attracted much attention because it has some gap in the transport. This is the, yes, in the usual configuration, the resonant states coexist with the other states. So even though the resonant state may not transport, provide a good transport channel, the other decoupled state may transport it. But of course, if we increase the interlayer interaction strength, then I said the two-way interlayer interaction opens a gap throughout the Pilkyung zone and it reveals the resonant state. In such a case, we will see some kind of the dynamic property of the resonant state alone. But yeah, I'm sorry, I didn't calculate it.
I see this. Another sort of related a chart to the center relating to the discussion we had just now. I suppose what you have shown is that you can prove that if the center exists, it has to be unique. But the existence is not guaranteed because of set theory, the cardinality.
Yeah.
But I suppose if you just put two layers on top of each other, there must be a point where the shift can be arbitrarily small, right? And it has to be smaller than any real number.
Yeah.
Yeah, so the delta can be arbitrarily small.
Arbitrarily small, but not zero. I'm distinguishing that difference.
Yes. So that means if I do an arbitrarily small shift, I can always have a system with a center.
Yes. No, not always. Yeah, right. Your understanding is correct. So even if there is no in the center, but there will be sufficiently, so as small as possible. So there will be almost infinitesimal delta at the supposed to be center. So if we move it, then we can make a center.
Is there any sort of physical measurement you can sort of be relevant to this very small shift? It's like a very small shift leading to a very large change of physical
No,
property.
I'm trying to find it, but we actually did this in. I didn't. We calculated this in a twisted biolographine with a 21 degree, and 21 degree with a different translation actually gives a completely different looking lattice structure.
Right.
But that difference does not make a noticeable energy difference. At maximum of 4 MeV or something like that. Of course, nowadays 4 MeV is still meaningful, but at that time we neglected it. And then recently, Alan McDonald calculated the carbon dioxide on top of hexagonal boron nitride. And the translational difference makes some noticeable difference.
Okay.
And long time ago, double wall nanotube system, there is the report on the difference of the same chirality, but different in-plane displacement give different physical result. Actually, double wall nanotube is simply the law of our twisted biology. But that difference is maximized it becomes clear in double wall nanotube because double wall nanotube have a definite cut line that allowed K-points.
Sure.
And if the band structure even slightly moves, you can identify the difference. So in a double wall nanotube, slight displacement, you can identify.
So the difference is like the charge density distribution or the charge?
Charge density, gap, and optical property, anything.
Okay, so a very small shift can lead to a very large signal.
Not very large,
Not very-
but a
noticeable.
noticeable difference.
But in the thing that you mentioned for in the mention for the carbon nanotube, if you make the carbon nanotube very big, is this still true? Like you can distinguish them?
Pardon?
In the case that you make the side the tube very big, can you still like distinguish different?
Actually, very big carbon nanotube actually collapse. But if you suppose it does not collapse, I think we can identify the in-plane displacement. And McDonald actually showed the displacement between hexagonal boron nitride plane, and carbon nanotube. The displacement gives a difference.
Yeah, I just wonder if you have such a resonance state in quasicrystals, and so what's the image in the real space? Have you plot that the wave function of those resonance state in real space?
So if you check the STM,
Right.
STS, then you will see that data. But in the general configuration of graphene quasicrystal, the resonance state coexists with the other states, the
Right.
non-localized graphene. So
Right.
it's just overlap. But if we use a different material or apply the pressure, then we can reveal so we see purely the.
Yeah, but what if I only plot the resonance state only? So the wave function, I guess will be around the center, right?
Yes, around the center, but that difference, as you can see from the.
So do you have such a plot, so we can get some feeling about it's spread over the real space?
Its difference is
Waiting for it. It's last year.
Yeah.
They can see the UST hosting measure the STM of TMB observing degree rotation. That actually the resonance state is very close to the top of the balance.
Very close to
The balance
which
you can see is MOS2. Yeah, then they show the STM signal of that. They publish the Nature.
I missed it. Yeah, I'm cleaning those. Yeah, so this would be so this is the exact center, and this would be so it would be quite difficult to distinguish the exact center and deviation.
So my actual question is, what is the localized? It's not localized, but the spread of the how big is the spread of the wave function in real space? What determines this decay length in real space? Maybe there's some also oscillation, like Friedel oscillation or something.
It's still composed of the in-plane, the infinite wave function in layer 1 and layer 2. In principle, it's not localized at all.
Oh, it's not localized at all.
Localized, not localized, but shows finite probability only along specific atoms. So
I
this
see.
side would be almost exact.
Thank you.
Just a general question, for example, one sheet of graphene in free space without a substrate is usually has some ripples, so it is like Duke reflection of volume. Just for education, what will be if we imagine bilayer with infinite lengths in the free space? What will be with the sheet?
Free space, we usually work on the substrate,
Yeah.
so we do not worry about it.
In the case of quasicrystal.
Yeah, quasicrystal. Free space, I think, but still, the bilayer is stiffer than the monolayer graphene, so the ripple effect will be weaker. Someone said that that's one of the reasons why we see offset of butterfly in bilayer graphene first, rather than monolayer graphene, but it depends.
So you discussed two different scenarios for the nonlinear features of the Landau levels.
Pardon?
You mentioned the case A and case B.
Yes.
Sort of continuous spectrum.
Yes.
The other one when you have two different. So in general, how would you distinguish those two cases from the shapes of the nonlinear version of the Landau level?
I introduced those two cases that we can apply this to the two different cases. So in the first case, we can use a well-known set of reference density of states and use it as a ruler or measure to measure the energy spacing. So that would be much easier. I'm sorry, not much easier. So experimentalists will not like much easier because it's not easier because we do not know the Fermi energy. We need to align them. And also, actually, I tried to propose this, but the energy spacing of usual 2D EG are not very, very different from that of monoray graphene. So it would be limited in some way. But anyway, so the graphene boron nitride happen to have two sets of Landau level. So and the energy spacing was really small. And which group? MIT group, Harvard group, the ones told me that they not in the moiré system, but in the scalar potential system, they show that such how can I say? At some point it touches, at some point it makes isolated event is quite common in the scalar potential superlattices. So in such a case, we may apply this to the system.
As one follow is then the relationship with the role of the open orbits here.
Yeah.
Whether you think it's crucial or you just need two different Fermi surfaces and two sets of
So open orbit usually provides a continuous energy levels. So yeah, but if we have a larger Fermi surface and smaller Fermi surface, two pockets, then we can apply this. But compared to the larger, compared to the open orbit, usually even if the orbit is large enough, that energy difference is not very completely different. But at least we can tell whether this scale is large, becomes larger or becomes smaller and so on.
I have a question. The quasi-bound model for 30-degree TVG, depending on the shift. So what if you give a shift, interlayer shift, how the Hamilton change?
It changed, but actually it does not. So
Yeah.
you know our band structure, the quasicrystalline level space, the far from the Dirac point.
Yeah, I mean, just wondering how this Hamiltonian change. So you put some phase factor and it's a unison transformation.
Yeah, you phase factor and but I didn't recover this to whether it. I think it's not exactly identical. We checked this in the chemistry biology.
Yeah, but non-structures
And the structures looks identical because of the small energy difference.
You have some difference, no, finite difference, but
infinitesimal difference.
infinitesimal, so that, I'm asking this, within that 12 waveform.
Within the 12
Yeah,
model,
yeah, I assume this is just connected by unitary transformation.
yeah, well, I didn't, I don't check this and didn't check the vendor structure because
This looks numerically different, but the
numerically
I think
different,
it's
small
some-
difference, I think. It's not exactly the transformable to delta equals 0 by unitary transformation. If our understanding in a TC value is correct. We change the delta, but it does not, it gives similar Hamiltonian by unitary transformation, but it's not exactly the same.
But if you commensurate, commensurate that would not true, but incommensurate,
Incommensurate.
it's the same, right?
Incommensurate.
Okay, let's take it later. The other question.
So with the profile of density state of the beta, you know about the topology of the Fermi surface, but with the full profile, can you say something about the geometry of the Fermi surface,
Geometry of the
like the shape of the Fermi surface, other than the topology?
shape, yeah, because the Landau level energy spacing only usually matters the area regardless of the shape. So with this, without any other clue, it's quite difficult to tell about the shape, whether it's isotropy or anisotropy. But of course, if we tilt it, then we change the Fermi surface, so we will be able to tell something. But it will be very
So with the beta, how can you say? But like you say that depend on the area of the Fermi surface, right?
What do you mean?
You mean that like the density of state will depend on the topology
Yeah.
of the Fermi surface. So you can distinguish
Area.
the continuous and the discontinuous. So that means the topology is closed and open. And you also say that you also depend on the area of the Fermi surface.
Yeah.
Then the beta density you also can distinguish or can like
Yeah.
determine the density as a.
Okay, so maybe you can continue.
Oh, yeah.
So let's end. Okay, so let's thank Pilkyung.